Welcome to today's session. We're diving into LeetCode problem number 617, merge two binary trees. This problem challenges us to combine two binary trees into one by merging their nodes recursively. It's a great exercise to deepen your understanding of recursion and tree traversal. Let's get started. In this problem, we are tasked with merging two binary trees, root 1 and root 2. Imagine overlaying one tree on top of the other. If two nodes from the trees overlap at the same position, we add their values together to create the value of the merged node. However, if a node exists in only one of the trees, that node will simply be part of the merged tree as is. The final output is the root of this new, merged binary tree. For the input, both trees are represented by their root nodes, and each node contains an integer value. The output will also be the root of the resulting merged binary tree. Let's look at an example to understand this process. Consider two binary trees as inputs. The first tree, root 1, has the structure: 1 is the root, with 3 as its left child and 2 as its right child. Additionally, 3 has a left child, 5. The second tree, root 2, has 2 as the root, with 1 as its left child and 3 as its right child. Furthermore, the left child, 1, has a right child, 4, and the right child, 3, has a right child, 7. These two trees will be merged according to the rules we just discussed. The resulting merged tree combines overlapping nodes by summing their values, and includes non-overlapping nodes as they are. Here, the root nodes, 1 and 2, are merged to form 3. The left children, 3 and 1, are merged to form 4, and the right children, 2 and 3, are merged to form 5. Moving deeper, the left child of 3 in the first tree, which is 5, remains as is because there's no overlapping node in the second tree. Similarly, the right child of 1 in the second tree, 4, and the right child of 3 in the second tree, 7, are added directly to the merged tree. The output for this example is a tree with the structure: 3 is the root, 4 and 5 as its left and right children, respectively, 5 and 4 as the left and right children of 4, and 7 is the right child of 5. The final output array representation of this tree is 3, 4, 5, 5, 4, null, 7. Now, let's consider another example where the first tree, root 1, contains just a single node with the value 1. The second tree, root 2, has 1 as the root, with 2 as its left child. When merging these trees, the root nodes, both 1, are added to produce 2 as the new root of the merged tree. The left child from the second tree, 2, remains as is because there's no corresponding node in the first tree. The resulting merged tree has 2 as the root and 2 as its left child, while the right child remains null. The output for this example is 2, 2. For the third example, the first tree, root 1, is empty, meaning it has no nodes. The second tree, root 2, contains a single node with the value 1. In this case, since one tree is empty, the merged tree is simply the non-empty tree. Therefore, the merged tree is identical to the second tree, with 1 as the root. The output array representation for this example is 1. Finally, let's review the constraints and edge cases to keep in mind. The number of nodes in both trees is limited to the range of 0 to 2000, and the value of each node can range from -10 to the power of 4 to 10 to the power of 4. Some specific edge cases include: if one of the trees is empty, the output will be the other tree; if both trees are empty, the output will also be empty. For trees with different depths, nodes from the deeper tree that don't overlap will appear in the merged tree as is. The solution must also handle negative values properly during the merge process. Additionally, if either of the trees contains only a single node, the output will reflect the appropriate merged value for that node. These considerations ensure that the solution accounts for a wide variety of scenarios in merging binary trees. To solve the problem of merging two binary trees, we first consider a recursive depth-first approach. Binary trees are inherently recursive structures, which makes this approach a natural fit. The idea is that we traverse both trees simultaneously and merge corresponding nodes. When both nodes exist, we sum their values to create a new node in the merged tree. If one of the nodes is null, we simply take the non-null node and use it directly. The process involves checking each pair of nodes, combining their values, and then recursively merging their left and right children. From a complexity perspective, this approach is efficient. The time complexity is O(n), where n is the number of nodes in the smaller tree, as we visit each node exactly once. The space complexity is O, H, or H is the height of the tree, due to the recursion stack. This makes the recursive approach both efficient and well-suited to the problem structure. The recursive depth-first approach has several advantages. It's intuitive, aligning naturally with the recursive design of binary trees, and it's straightforward to implement. However, one downside is the risk of a stack overflow if the tree is extremely deep, as the recursion stack grows with the height of the tree. To address this limitation, we can consider an alternative iterative breadth-first approach using a queue. Here, instead of recursion, we use a queue to traverse the trees level by level. This avoids stack overflow issues and provides more control over the traversal order. The process begins by initializing a queue with pairs of corresponding nodes from both trees. For each pair, if both nodes exist, we sum their values. If one node is null, we directly link the non-null node to the merged tree. We then enqueue the children of both nodes to continue the merging process. This method ensures that all levels of the tree are processed iteratively and systematically. In terms of complexity, the iterative breadth-first approach has a similar time complexity of O, n, where n is the number of nodes in the smaller tree, as we still visit each node exactly once. However, it has a space complexity of O, n, due to the queue, which stores pairs of nodes during the traversal. This approach has the benefit of avoiding the recursion stack, making it safer for extremely deep trees. It also offers fine-grained control over the traversal order, which might be useful in certain scenarios. On the downside, it's slightly more complex to implement than the recursive approach and requires additional memory for the queue. Another alternative is to create a completely new tree during the merge process. While this ensures the original trees remain unmodified, it's less efficient and requires significant additional memory. Given that modifying one of the input trees is allowed for this problem, this alternative is generally unnecessary. After evaluating the options, the recursive depth-first merge approach is the chosen strategy for solving this problem. It's simple, aligns naturally with the recursive structure of binary trees, and offers optimal time and space complexity in most cases. While the iterative approach addresses stack overflow concerns, it introduces additional complexity and memory usage. For most practical scenarios, the recursive approach strikes the right balance between simplicity and efficiency. Key observations include the fact that the recursive nature of binary trees makes this approach both elegant and intuitive. By traversing both trees simultaneously, we ensure efficient merging without unnecessary overhead. Additionally, avoiding side effects on the original trees is not a requirement for this problem, which simplifies the implementation further. While iterative or alternative approaches may be better suited to specific edge cases, the recursive depth-first strategy is the most practical and effective solution for this particular problem. The problem involves merging two binary trees such that the resulting tree is formed by summing the values of corresponding nodes from the input trees. If a node exists in only one of the trees, we simply use the non-null node as it is. To solve this, we use a recursive algorithm. First, we handle the base cases. If both nodes are null, there's nothing to merge, so we return null. If just one of the nodes is null, we return the other node, preserving the existing structure of the non-null tree. Next, for non-null nodes, we create a new node by summing their values, then recursively merge their left and right children to construct the left and right subtrees of the new node. Finally, we return the merged node, which becomes the root of the new tree. Binary trees are inherently recursive in nature since each subtree is a binary tree itself. This makes recursion a natural fit for the algorithm. The approach carefully handles null nodes to ensure that non-null subtrees are preserved in the merged result. Additionally, the algorithm is efficient in terms of memory usage because it reuses nodes from the input trees rather than creating unnecessary copies. The data structure we work with here is a binary tree node, which consists of a value and pointers to its left and right children. To start the algorithm, we take the root nodes of the two input trees. If one of the root nodes is null, we simply return the other root. Otherwise, we proceed to merge the current nodes. For non-null root nodes, we create a new node with its value equal to the sum of the values from the two input nodes. This new node will form part of the resulting tree. Then, we make recursive calls to merge the left children of the two input nodes and assign the result to the left child of the new node. Similarly, we merge the right children and assign the result to the right child of the new node. Once this process is complete, we return the newly created node. It's important to consider edge cases. If both input trees are empty, the result is also an empty tree. If one tree is significantly smaller than the other, the algorithm ensures that the structure of the larger tree is preserved wherever there are no overlapping nodes. The Python implementation of this algorithm is straightforward. We begin by checking for null root nodes and handling them as base cases. The implementation continues by modifying the value of the first tree's root node to include the sum of both root values. The algorithm then makes recursive calls to merge the left and right subtrees, effectively building the merged tree in place. Finally, the root of the modified tree is returned as the result. The time complexity of this approach is O(n), where n is the total number of nodes in the smaller tree, as each node is visited exactly once. The space complexity is O(h), where h is the height of the tree, representing the maximum depth of the recursion stack. Reusing the nodes from the original trees minimizes memory overhead, making the solution efficient. While tail recursive optimizations could further improve the algorithm, Python does not optimize for tail recursion. To help visualize the process, consider the example trees provided. In the first tree, the root node has a value of 1, with left and right children 3 and 2, respectively, and a left child of 3 having another left child with the value 5. In the second tree, the root node has a value of 2, with left and right children 1 and 3. The left child of 1 has a right child with the value 4, and the right child of 3 has a right child with the value 7. The resulting merged tree is constructed by summing the values of overlapping nodes. For example, the root nodes are merged to form a value of 3. The left subtree is formed by merging the values 3 and 1, and the right subtree is formed by merging 2 and 3. For nodes where one tree has a value but the other does not, such as the 5 in the left subtree of the first tree or the 4 in the right subtree of the second tree, the non-null value is carried forward to the merged tree. In the right subtree of the merged tree, the nodes with values 2 and 3 are summed to form 5. Additionally, the right child of the second tree's right node, with a value of 7, is carried forward as there is no corresponding node in the first tree. The final merged tree has a root node with the value 3, a left child with the value 4, and a right child with the value 5. The left subtree contains nodes with values 5 and 4, while the right subtree ends with a node having the value 7. This example demonstrates how the algorithm handles node sums, null nodes, and the structure of the resulting tree, highlighting its efficiency and correctness. The given code solves the problem of merging two binary trees. Each corresponding node in the input trees is combined to form a new tree, where the value of each node is the sum of the values of the corresponding nodes in the input trees. If a node exists in only one of the trees, it is used as is in the merged tree. First, we define a tree node class, which represents the structure of a binary tree node. Each node has a val attribute for its value and left and right attributes pointing to its child nodes. The mergeTrees function is implemented within the solution class. This function takes two input nodes, root 1 and root 2, representing the roots of the two binary trees that need to be merged. The base cases are handled first. 1. If root 1 is null, none, the function immediately returns root 2. This means that if the first tree is empty, the second tree is used directly. 2. Similarly, if root 2 is null, the function returns root 1. If both nodes are non-null, their values are added together, root1.val plus equals root2.val. This step merges the values of the two nodes. Next, the function recursively merges the left and right child nodes of root 1 and root 2. The results of these recursive calls are assigned to root1.left and root1.right, respectively. This ensures that the entire tree structure is processed and merged. Finally, the function returns the modified root1, which now represents the root of the merged tree. The recursion ensures that the entire tree is processed, and the base cases handle scenarios where one of the trees is partially or completely empty. This solution efficiently handles the merging of two binary trees and operates with a time complexity of O(n), where n is the total number of nodes in the smaller tree, as each node is visited once. Here, we begin by defining the structure of a binary tree node using the treenode class. Each node has an integer value, a reference to a left child, and a reference to a right child. There are three constructors provided: a default constructor for creating an empty node, a constructor that initializes the node with a value, and another that initializes the node with a value as well as left and right child nodes. This flexibility allows us to create nodes and trees in different configurations. Next, we define the solution class, where the mergeTrees method is implemented. This method takes two tree node objects, root1 and root2, representing the roots of two binary trees. In the first part of the method, we handle the base cases. If either of the trees is null, we simply return the other tree. For instance, if root1 is null, we return root2 because there's nothing to merge from root1 in that case. Similarly, if root2 is null, we return root1. Now, if neither of the trees is null, we proceed to merge them. The first step is to combine the values of the two nodes. We do this by adding root2's value to root1's value, effectively updating root1 to reflect the merged value. After merging the current nodes, we use recursion to handle the left and right subtrees. The left child of root1 is updated by merging the left children of root1 and root2, and similarly, the right child of root1 is updated by merging their right children. This recursive approach ensures that we traverse and merge the entire structure of both trees. Finally, we return root1, which now represents the root of the merged tree. This method elegantly handles the merging process by combining values at each node and recursively descending through the tree structure. Here, we start with two input binary trees. Tree 1 has its root value as 1, and tree 2 has its root value as 2. The first step involves merging these root nodes, which gives us the new root value of 3, calculated as 1 plus 2. Next, we move to the left children of the roots. The left child of tree 1 has a value of 3, and the left child of tree 2 has a value of 1. Adding these together gives us a new left child value of 4 for the merged tree. Then, we continue down to the left of this node. On the left side of tree 1, we have a value of 5, but tree 2 has no corresponding node, meaning it's none. In this case, we simply retain the existing node from tree 1, so the leftmost child of the merged tree remains 5. Now, we look at the right child of the node with value 4. Tree 1 has no right child at this position, but tree 2 provides a node with a value of 4. Because tree 1's node is none, we take tree 2's node as is, setting the right child of this branch to 4. Shifting focus to the right child of the root, tree 1 has a value of 2, and tree 2 has a value of 3. Adding these gives us 5 for the merged tree's right child. Both trees lack a left child at this position, so the left child remains none. However, the right child of tree 2 has a value of 7, while tree 1 has no corresponding node. Since the node in tree 1 is none, we use the node from tree 2, resulting in a right child value of 7. The final merged tree is now fully constructed, with nodes arranged as shown. In this example, we examine trees with unequal depths. Tree 1 has a root value of 1 and a left child with a value of 3, but no right child. Tree 2 has a root value of 2, but no left child. The roots are added first, giving a new root value of 3. For the left child, tree 1 has a node with a value of 3, while tree 2 has no corresponding node. Since tree 2's left child is none, we keep tree 1's left child as is. As for the right child, neither tree has a node in this position, so the right child in the merged tree remains none. The result is a tree with a root value of 3 and only a left child with a value of 3. Here, we see the final merged tree for the previous example, a simple structure with a root value of 3 and a left child value of 3. Now, moving to the next case, we handle scenarios where one of the input trees is completely none. For instance, tree 1 is none, while tree 2 is a complete binary tree with a root value of 1, a left child of 2, and a right child of 3. The merging process begins at the root. Since tree 1 doesn't have a node, we directly use tree 2 as it is. When one of the trees is none, the other tree is returned unchanged. In this case, the result is simply tree 2, which remains intact with its root value of 1, left child value of 2, and right child value of 3. This scenario highlights an important rule: if either node in the recursion is none, we return the other node. Additionally, when both nodes are present, their values are added together, and recursion ensures that all subtrees are merged correctly. With this understanding, you now have the tools to merge binary trees effectively, no matter their structure. To understand the time complexity of merging two binary trees, we start by analyzing how the algorithm processes the nodes. The merge trees function operates recursively, visiting each node in both trees exactly once. At each node, it performs a fixed amount of work. Specifically, it adds the values of the two nodes together and makes recursive calls to process the left and right children. Let's denote the total number of nodes in the larger of the two trees as n. Since each node is visited exactly once and the work done at each node is constant, the overall time complexity is O, n. This means the runtime scales linearly with the number of nodes in the larger tree, making the algorithm efficient in terms of time complexity. Now let's analyze the space complexity, which is influenced by the memory used for the recursion stack. The depth of the recursion stack depends on the height of the binary tree. In the best case, where the trees are perfectly balanced, the height of the tree is proportional to log n, and the recursion stack requires O log n space. On the other hand, in the worst case, when the tree is completely skewed like a linked list, the height becomes n, and the space usage grows to O n. Thus, the space complexity is O h, where h represents the height of the larger tree. This shows how the structure of the tree impacts the memory usage of the algorithm. Next, let's break down the best, average, and worst case scenarios to understand how the algorithm performs under different conditions. In the best case, when both trees are balanced, the recursion stack depth is O log n, and the time complexity remains O n. In the average case, where the trees are moderately balanced, the recursion stack depth is typically O log n as well, and the time complexity is still O n. In the worst case, where the trees are skewed, the recursion stack depth increases to O n, but the time complexity remains O n. Comparing this solution to a naive approach highlights its efficiency. A naive solution might involve creating a new tree and traversing both input trees to populate it, which would require O n extra auxiliary space. In contrast, this optimized approach modifies the first tree in place, minimizing auxiliary space usage. It only uses O h space for the recursion stack and O 1 additional memory for computations. Finally, let's solidify our understanding with a mathematical proof for the big O complexities. For time complexity, the algorithm traverses each node exactly once, which gives us O n, where n is the number of nodes in the larger tree. The constant amount of work performed per node, such as value addition, does not change this overall linear complexity. For space complexity, the recursion stack depth determines the memory usage. In the worst case of a skewed tree, the height equals the number of nodes, so the space complexity becomes O n. In the best case of a balanced tree, the height is proportional to log n, leading to a space complexity of O log n. This analysis confirms that the solution is both time and space efficient, with optimal use of the recursion stack and no additional memory allocation for new nodes. When solving problems like merging binary trees, there are some common mistakes to watch out for. First, not handling null nodes properly can lead to runtime errors. If either of the input trees has a null node at any point, your code must account for this by including base cases to handle null trees gracefully. Another issue is modifying the input trees directly instead of creating a new merged tree. In some variations of the problem, modifying the inputs can cause unintended side effects, especially if those trees are being used elsewhere in the program. Efficiency is another area where mistakes happen. For recursive solutions, failing to optimize the traversal can result in unnecessary recomputations. For instance, if you're not reusing computed values in a memoization-based approach, the time complexity can increase significantly. Additionally, overlooking edge cases is a frequent pitfall. Scenarios like one tree being empty, both trees consisting of just one node, or trees having significantly different depths can lead to incorrect results if not explicitly handled. Lastly, overcomplicating your solution by introducing unnecessary data structures or operations can make the code harder to understand and less efficient. Always aim for the simplest approach that solves the problem effectively. Now, let's look at some key insights for interviews. Binary tree problems often involve recognizing patterns in recursion or traversal techniques. For example, knowing when to use pre-order, in-order, or post-order traversal can make a big difference in solving the problem efficiently. There are also trade-offs to consider between space and time. Recursive solutions, while straightforward, use O, h space for the call stack, where h is the tree's height. Iterative solutions can reduce this space usage by managing the stack explicitly, but they may require more code. Edge cases are another area to focus on during interviews. Be prepared to handle scenarios like empty trees, highly unbalanced trees, or very deep trees, as interviewers often test these situations explicitly. Beyond coding, it's important to communicate your thought process clearly. Explain why you chose a particular approach, highlight its trade-offs, and demonstrate awareness of alternative solutions. Speaking of related problems, this problem is a direct application of recursive tree traversal. You might also encounter similar problems like inverting a binary tree, calculating the diameter of a tree, or checking path sums, all of which require variations of traversal and logical checks. Finally, let's explore some alternative approaches to solving this problem. One option is using an iterative depth-first search. Instead of relying on recursion, you can manage the traversal explicitly with a stack. This avoids potential issues like call stack overflow for very deep trees. However, the trade-off is that you'll need additional code to handle stack management. Another approach is breadth-first search, which uses a queue to traverse the tree level by level. This can be particularly useful for problems with level-specific constraints, but it typically requires more memory, as the space complexity is O(W), where W is the maximum width of the tree. Lastly, a divide-and-conquer strategy can be effective in some variations. By breaking the problem into smaller subproblems and combining the results, you may achieve better efficiency. However, this method often requires additional merging logic, which can increase the complexity of your solution. Choosing the right approach depends on the specific constraints and requirements of the problem you're tackling. Great job! We explored a recursive approach to merge two binary trees efficiently. Remember, recursion is a go-to strategy for tree problems, and mastering it will serve you well in interviews and real-world scenarios. Don't forget to practice regularly and apply these concepts to similar challenges. Thanks for joining, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!